Welcome to the fourth video on graphing conic sections. Here we study the hyperbola. If you're not familiar with the algebra process called completing the square, you're going to need to do that before you make any sense out of the algebra you'll see in this video. You can go to my YouTube channel, Recedlo Math, and check it out, or there are many other places you can find it. Assuming that you're comfortable with completing the square, let's continue. Let's start out with some hyperbola vocabulary. A hyperbola consists of two opposing branches. It may look like this is the graph of two parabolas or just two things in general, but it's actually the graph of one single equation. And a hyperbola can either open sideways, to speak loosely about it, as you see here, or it can open in an upward and downward fashion, as you see here. Let's go back to the sideways one for a minute and get some more vocabulary. The two turning points of the hyperbola are called vertices. In addition to turning and facing away from each other, the two branches are bound by invisible lines that aren't themselves part of the graph, called asymptotes. The graph of this hyperbola would continue to extend to the left and right and would never cross or even touch these two invisible lines or asymptotes. And when I say that they're invisible, what I mean is they're not part of the hyperbola, but they're there guiding its direction. And in between the two vertices is a point that's not on the hyperbola either, but we call that the center. Now, for graphing purposes, here's the philosophy that guides us when we graph a hyperbola, which we'll see here in a few minutes. If we can find the location of the center, and we can find the slope of the asymptotes, then we'll essentially have a framework that holds this hyperbola in place. And if then, as a third component, I can find the distance from the center to the vertices, then I'll essentially have an exact known location for my hyperbola. Hyperbolas, as we mentioned, can also go in an upward-downward opening fashion as well. And if I can tell which direction it's opening, the center, the slope of the asymptotes, and how far away the vertex is from the center in each case, again, I'll have an exact known location of all the important characteristics of the hyperbola. But in order to find these characteristics, I need my equation to have a preferred format. And that's quite often not initially the case. Quite often when we're given a conic section, we're given something in standard form, as you can see here. Now, in general, we can say about standard form that we're going to have a hyperbola whenever a times b has a negative result. That doesn't mean a and b are both negative. It means the product of a and b is a negative number. And we'll look more at that situation later. But let's focus now on these so-called preferred formats. And before we do a conversion from standard form into a preferred format, let's take a look at the first of the two and a specific example where the hyperbola equation is already given to us in that format. Again, that's not always the case and quite often won't be, but let's start there, just so I can share some basic mathematical discoveries with you that you'll then be able to use yourselves. So in order to graph this thing, mathematicians have made some amazing discoveries, and I'm going to give you the end result, sort of the final versions of those discoveries, and not take you through the long history of how it was that they came about. Hopefully you can use some of these discoveries on your own to graph hyperbolas. And what mathematicians discovered is that when a hyperbola is in exactly this format as you see it here, then we can tell what the center of the hyperbola is going to be just by taking the opposite of the completed square numbers, just like we did with the other conic sections. So we now know that the center of this hyperbola is going to be at the point -1, -4. Here's another discovery mathematicians have made. They discovered that if the hyperbola equation starts with the letter x, that you're going to get a sideways hyperbola. In other words, it's going to open from left to right and right to left when we look at the two branches. And furthermore, mathematicians have figured out that if you take the radical of the first denominator, in this case radical 9 being 3, you will then have the distance from the center to the two vertices of the hyperbola. Now there are lots of reasons why, and this video doesn't go into those. But suffice it to say, that was a discovery that's made, and you can capitalize on that discovery yourselves while graphing. Another discovery was made when taking the radical of the second denominator, in this case radical 4 is 2, that when you take the ratio of those denominators, that number, plus or minus that number I should say, will be the slopes of the two asymptotes. So all I have to do now is draw lines through the center, one with a slope of 2/3 and the other with a slope of -2/3. And I now have the two asymptotes of the hyperbola. Now, knowing that the hyperbola opens from left to right and right to left, and that it's bound by these asymptotes and must turn at the two vertices, I now know exactly where this hyperbola is, and I can get a pretty good image of its graph by just having used those mathematical discoveries from centuries ago. Let's take a look at another hyperbola, this time in the preferred format where the y is first. For example, suppose we were told to graph this particular hyperbola here. We can use the mathematical discoveries mentioned earlier to piece together all the information we need to know pretty much precisely where this hyperbola is going to graph out. Again, it comes down to these four particular numbers. In this case, -1, +3, 25, and 16. Just as before, we can take the numbers inside the completed squares, switch their signs, and get the center of the hyperbola. Further, because this hyperbola starts with a y as its first term, mathematicians have discovered that the hyperbola is going to open upward and downward. In other words, have two branches, one opening upward and one opening downward. Furthermore, we've discovered if we radical the first denominator, in this case radical 25 is 5, we can get the distance from the center to each of the vertices. And if we then radical the second denominator and take the ratio of those radicals, we will have the plus or minus slope of the two asymptotes. So what I'm going to do now is draw two lines through the center, one with a slope of 5/4 and one with a slope of -5/4. And once I have the center, the vertices, and the asymptotes, I know exactly which direction this hyperbola is going, I know exactly where it turns around, and I also know what space it's confined to by the asymptotes graphed here. Putting all that together gives me a pretty accurate picture that the hyperbola will be right here. But, of course, the big question is, what do we do if our section or hyperbola is not in the preferred format? What if it's in standard form, as you see in the upper portion of your screen? such as this particular example. Well, then much like the other conic sections, we have to use our algebra skills to convert this into a preferred format. And then we can discern all the information we need about the hyperbola. First, let's notice that a times b, or 4 times -9, is -36. And since a times b is negative, then we essentially know that we have a hyperbola here. But still, I don't have it in the preferred format. So we're going to use the same completing the square trick that we've used in all the other conic sections to get this into a preferred format. The first thing I did here was put my x terms together and my y terms together. Then, to make completing the square easier, I started by factoring out the lead coefficient of the x's and separately factoring out the lead coefficient of y squared, giving me this. You may want to hit pause and confirm the algebra in your head. And now that I've done this, I now have, inside both pairs of parentheses, I have what will turn out to be a monic trinomial once the square is completed. And so I can now concentrate on completing the square only on what's inside of the parentheses. That I've done here. Once again, you may want to pause here or even go back and watch a completing the square video if need be. But now that I'm done completing the square, which is really the bulk of the work here, I can now distribute the 4 and -9 that I once factored out. So distributing the 4 and the -9 ultimately brings me to a place where I'm getting closer to the preferred format. Next, I did some simple algebra. I merely combined the -4 and the +144, and then subtracted 140 from both sides. But I'm still not in the so-called preferred format for a hyperbola. I'm close to it though. Notice, however, that on the right side of my equation I have a 36, and to be in preferred form, that number needs to be a 1. And so it makes sense to me to divide every term in the equation by 36, thus giving me the 1 on the right side that I need. Notice on the left side of the equation, I reduced the fraction 4/36 to 1/9 and 9/36 to 1/4. And I now have the preferred format of the hyperbola. And what I mean by preferred format is that format through which we can discern the center, the vertices, and the slope of the asymptotes. Just as we did before, in fact, this is literally the problem we did before, we can discern that the center is -1, -4, again, switching the signs on the completed squares. Thus, putting our center here, and just as we did before, taking the radical of the first number and realizing that the vertices will be, in this case, 3 spaces to the right or left, because we have an x first hyperbola here. Again, taking the radical of the next denominator, and the ratio of those radicals leads me to the slope of the asymptotes. You've seen all this before, earlier in this video. And ultimately, knowing the asymptotes, center, and vertices, I have a pretty decent idea where the hyperbola will be, and that's my graph. Let's take a look at our final example here. Suppose we were trying to graph this conic section. First of all, notice that 25 times -16, or a times b, is definitely a negative number, and therefore strong reason to believe that we have a hyperbola here. So, as usual, I would rearrange my terms, putting my x terms together and my y terms together, along with my constant on the other side. This enables me to complete the square and ultimately get this hyperbola into preferred format so I can figure out some things about the graph. So just as before, I would factor out the lead coefficient of x squared and factor out the lead coefficient of y squared. And once that's done, I would once again go about the business of completing the square on each of the polynomials in the parentheses. So completing the square on each of those yields this. And once the squares are completed, I can then distribute the same numbers I factored out earlier and I'm now that much closer to getting this thing in a preferred format. First, I decided to combine the negative 225 and the positive 16. Then I added 209 to both sides and realized I'm now even closer to preferred format. But one thing that differs is that this term should be a 1 in preferred format. To make that term a 1, I divided the entire equation by negative 400, thus not only giving me the 1 on the right side that I want, but some simplified expressions on the left side. I didn't show the work here, but I did reduce the fraction 25/400 to 1/16 and 16/400 to 1/25. Now technically, this is not preferred format because it starts with a term whose coefficient is negative. Preferred format is the subtraction format. So now I'm going to reverse the two terms on the left. I haven't changed anything mathematically, but what I've done is I've converted this into the typical format that we want when we want to discern things about the hyperbola. In other words, I've turned it into fraction minus fraction equals 1. And now that that's done, I'm in a great position to graph this. This is actually a problem we saw earlier in this video. And so I'll remind you that we looked at the equation here, saw the numbers inside the completed squares, and in the process of graphing, thereby deduced the center. Once we knew the center of the hyperbola, we took the radical of the first denominator, which is under the y term, you'll notice, thus letting me know that 5 is the vertical distance to my two vertices. None of this should seem terribly new to you as you saw it earlier. Furthermore, taking the radical of the second denominator and then the ratio of those radicals tells me the slope of the asymptotes, and so I drew two asymptotes there. And once I have the center, the vertices, and the asymptotes, I pretty much have a clear picture of where this hyperbola is going, and the graph is finished. And that completes this video and this 4-video series on conic sections. Thank you again so much for watching.